Hi, I'm James McAndrew, Senior Simulation Engineer at Generative Engineering. In this demo, I'll show how we use our product to optimize a bioreactor impeller, maximizing mixing while keeping shear within safe limits for shear-sensitive cultures. To do this, we link a parametric CAD model of the bioreactor to a CFD simulation template. In this transient simulation, we initialize a passive scaler at the bottom of the vessel and track how quickly and uniformly it becomes distributed throughout the tank. Now I'll show you the experiment setup. On the left are the input parameters. We have CAD parameters such as blade count and blade pitch, and a simulation parameter, the impeller rotational speed. On the right are the target values. In this study, we maximize two mixing metrics that quantify homogeneity, plus a peak shear constraint of less than or equal to 0.5 pascals. We then run a multi-parameter optimization. The product automatically generates each geometry, meshes it, sets up the simulation, runs it, and performs post-processing. It iterates automatically through the design space, optimizing towards the target values. Here we're running 5 simulations in parallel, and we can click Generate Designs to begin the experiment. We can have a look at some previous results. We have over 100 fully evaluated designs. Each column shows a complete design with a CAD model, simulation performed, and post-processing. The mixing, the time history plots show how the mixing metrics evolve, and we can also see how quickly designs reach this mixing criterion. The passive scalar contour plots show the final concentration distribution. Purple regions are over-concentrated, yellow are under-concentrated. For shear, the peak value is reported, and a contour plot produced, where any regions exceeding 0.5 pascals are in dark red, for example here. So you can clearly identify any constraint violations. We also monitor numerical quality indicators such as the Courant number and the Y+ value to flag any outliers. We can also plot the parameters against each other to understand correlations and trade-offs. If we plot shear stress and mixed volume fraction against expiration time, we can see how the optimization evolved. You can see the expiration quickly moves into a feasible shear stress region below 0.5 pascals. Filtering to only the designs within this shear limit, and rotating the plot, we see the mixed volume fraction converging towards 1, improving from approximately 0.05 or remaining within the shear limit. Each of these points is a design, so we can select them and view details such as contour plots and CAD models. If we now examine impeller height against the mixing metrics, a clear trend emerges. Raising the impeller improves mixing performance. This is a strong design lever. Plotting rotational speed against shear stress, if we look here, this shows that the speed is the dominant driver of shear in the fluid. That gives us a practical operating window. Speeds that achieve high mixing without exceeding the shear limit. In a traditional workflow, exploring this design space would require extensive manual setup and many iterations. Here, a single parametric model and simulation template enabled automated exploration of the design space, optimizing the design and identifying key design levers.